my thesis research at San Diego State University that I did for my master's program. And we found some pretty interesting results. So I hope you think so as well. So let's start at the beginning with binary stars. Here we go. So a binary star system is two stars at once, kind of in the same place. They orbit each other just like the Earth orbits the sun. They share a common center of gravity. And ideally, in these systems, the orbits are perfectly circular. We call those Keplerian orbits. The forces are mainly from just gravity. And if we can monitor the interactions between these bodies, if we can trace their orbit out, we can extract good scientific information from that and learn more about these systems and how we can apply that to other systems as well. So over here on the right, here's a quick diagram of a binary orbit. The main body is going to be in the center here. That's not really identified. And the body circling it is over here. There's a lot of things here that can describe the orbit, but the one that we're going to focus on today is the argument of periapsis, this omega, the lowercase Greek letter omega here. This is also called the argument of periastron, or the line of apsides. It has many names, but they all mean the same thing. And it's kind of like the pointing direction of the orbit. So we'll come back to that in just a little bit. So we've got binary stars. Let's move on to eclipsing binary stars. Eclipsing binary stars happen when the orientation of that orbit from our perspective is just so that the stars will pass in front of each other, just like the moon passes in front of the sun or the Earth passes in front of the moon, and we see an eclipse. These stars will eclipse each other as well. Let's play this guy again. What we can do is we can measure the total flux or the total brightness from that system over time and display it in what we call a light curve. So we can see that here, the total brightness dips as one of the stars is blocked by the other one. And we can see this nice decrease in brightness that's easy to identify. What we can do is we can record consecutive events. We can watch these happen over and over and over again. And we can determine the orbital period of the system. How long does it take these stars to orbit each other? Which is a very important parameter. It's one of the basic parameters of these binary orbits. And we can describe that here in this linear fashion. You don't really have to worry about what these symbols mean. But if you've ever done any algebra, you can kind of imagine this is like y equals mx plus b. It's just a straight line. And we're going to compare that straight line to observations and models. So now we've got eclipsing binaries. We can figure out their orbital period. We can set up their orbits. And now we want to investigate the apsidal motion of these systems. So I mentioned earlier that the idealized orbit is circular, but as it turns out, reality has other things in mind. Real orbits are elliptical, which is kind of like a squished circle. And it's not just gravity that's contributing to the forces in this orbit. There's extra things that come from tidal forces. So like a different part of one star may pull on a certain part of this other one. And there's all of these cross-pointing effects and things because these bodies aren't just point sources. We can also think about general relativity as they are warping space-time. That has an effect in the apsidal motion. And then if you have a third body in the system, talking about binary stars, but you can also have triple star systems, 4-star systems or more, and those will add an additional gravitational force to the system. So what happens is that these orbits are no longer closed and they're not circular. So over time, we see this kind of spirograph motion as this orbit, this elliptical orbit itself, is rotating. And that's the apsidal motion. If we were going to draw the line, the argument of periastron through this orbit, kind of along the long axis, we would see it sweeping across. And that's exactly what this omega dot value here is. That's the argument of periastron, but it's change over time. And so if we can observe that, and we know the orbital period, we can figure out the apsidal period, how long it takes the entire orbit itself to rotate. So that's pretty great. Previous attempts to investigate the apsidal motion have been generally successful, but they only use an approximation of two values, which we are calling the internal structure constants. And these are the important ones that we're looking for here. We call them K21 and K22 for the K2-1 for the primary star, K2-2 for the secondary. And what they tell us is the density distribution inside the star. So is the mass concentrated more in the center? Is it more evenly distributed throughout that volume of the star? And this is really important because it gives us information about what's going on, not just on the surface, but inside of these stars where we can't actually see. But by observing this apsidal motion, we can determine that. So our new method is computing the individual constants. Those are the important ones that we're looking at here, using the eclipsing light curve program, or ELC. And so based on a set of input parameters for these orbits, we can march these things through time, and ELC will produce expected times of eclipse. So we can create a model, and the model says the star will eclipse at this time. Great work. So what we do is for 5 systems, YSIG, EMCAR, DRVOL, CWSEP, and V526 SGR, we use input parameters, initial parameters from previously published work, things that are generally accepted, and we collect times of eclipse from the literature, as well as the Transiting Exoplanet Survey Satellite, or the TESS mission. It's gotten some really good photometric data that we can use. Over here on the right is a cool diagram of the Carina Nebula, a very bright region, star-forming region in the southern sky, which we don't really see here from San Diego, but the TESS satellite and other people are looking at the southern sky as well. And our star EMCAR is up here in this kind of blue cross area. This is the most exciting picture that I found. The other ones are kind of just out in space. All right, so now we've got our systems, we've got our collected times of eclipse, we can run these models and compare them together. So we do just that. We use the ELC program, we compute these expected times of eclipse, and we compare them to both the observed times and then our linear, like y equals mx plus b eclipse line. If it's an ideal orbit, it's circular. So that would give us a line flat at 0. And then we compare these values in what we call the common period O minus C, or CPOC, common period O minus C diagram. So that's observed minus computed. So we take the observed values, we take our computed values, we compare them, and we want a really small number when we subtract the two of them. So we're going to make this plot a little bit bigger so we can really dig into it. Awesome. So just to start, again, that idealized perfectly circular orbit where the eclipses come around on time, they are regular, very expected, that would give us a line flat at 0 here. But again, our orbits are elliptical, there's extra forces. That doesn't really happen, especially on these short period and rapid apsidal motion binaries. So what we do is we collect these times of eclipse, the data points. We've got the black are the primary data points, the red are the secondary data points for the more massive and less massive stars in the system. We've got data for this system going back to the late 1800s. So we've got more than 100 years of eclipses here, which is pretty great. And so we've got our data points, and then we also have these solid curves. And those are the models that we have generated using the eclipsing light curve program. And it's been optimized such that we change the input parameters by just a little bit here and there, trying to get these curves closer and closer to as many data points as possible. And if we can get them as close as possible, as far as we can go, that will be our best fit system. We can see that down here in the residuals. They're all clustered around 0. Some of the older data points are a little bit more spread out, but as we get better and better, more modern data, we can see that they're much closer to 0, which is good. That just means our model is very close to the observations, and we've done a good job. This was one of our 5 systems. Another one, EMCAR, I've been talking about that one for a little bit. We don't have quite as much data, but we've got a really good fit to the system here. The residuals are small. They're within about 2 minutes, which is really nice. And we can see up here on the top, we've got our observed data points and our models, and they're all very close together. Looks pretty good. But I mentioned third bodies in the system earlier, or multiple bodies. What happens to this visualization when there's another force in the system? Well, lucky for you guys, we studied a 3-body system, the DRVOL system. And Here's the CPOC for that one. It looks a little bit different. We can see some similar behavior. We've got these black and red curves kind of oscillating through each other. That's the binary, the main part of the system. But we can also see this larger curve kind of hidden within the curve. So we see a peak around 1940 and another one maybe somewhere around like 2008 or so. And so that's the force from the third body perturbing this orbit, giving us another signal in here. So if we were going to extend this another 70 years or so, we would see another dip come up to another peak. We can use that directly to find how long it takes that third body to orbit that binary system, which is really great. Just by looking at eclipses, you can extract lots of information. Okay, how we doing? Doing pretty good. So for these systems, we've computed all of these values. What about the results? Do they make sense? Are they consistent? And the good news is our computed physical and orbital parameters are generally consistent with published values. One small hiccup we observed was that our models show that first system I showed you guys, Y sig, our model value for the radius is a little bit smaller for the secondary star. And that might be a result of stellar rotation or like a misalignment of the orbit axis. So the star, we assume that the stars are like kind of pointing the same way when they orbit. One of them might be offset by a little bit, and that could have an effect on the computation. Another thing we wanted to look at was the average of the apsidal constants, right? We are computing the individuals. What we can do is we can add them up, divide by 2, find their average, and we can compare that to that analytical approximation that has been done in previous apsidal motion studies. And good news, again, they are in good agreement. Our values, the average of our values is in good agreement with the average found with a completely different and independent method. So that's a nice result there. However, one thing to note is that the individual apsidal parameters are not always very close to the average, right? So for example, down here, we've got the average is negative 2.259, where the individuals are 2.0, 2.1, and about 2.54. This is in log scale, so the average looks a little bit different. But the thing is that these values are not always exactly close to this one, the average. Another thing we can look at here is that our input, we've got input values and output values for the EM car system, the very massive one. 21.42 is pretty darn close to 21.476. 22.89 is pretty close to 22.985. And if you look at these error bars, they are self-consistent. So our results are good. Great. We're testing this new method and we have these results that are consistent. But how do we know if these results are self-consistent, if they're actually correct? We're testing this new method. What if there's a bug that's just saying magically, here's the right answer? Maybe there's something else going on. So we need to check these things. What we can do is we can run a few tests. We can verify our results using what is called the F test, where from our best fit model, we can take the best fit values, plug it back in as an initial model, and ideally you would get those best fit values back, right? You give it the true values, it should return the true values. And it does, so that's good. We can verify our results that way. We also implement another kind of test. We do some optimization as we're getting those models close to the data points to make sure that those are self-consistent. And another method to compute the apsidal motion of the whole system is by doing what is called a Lohm-Scargel algorithm, which just says from a set of data points, it finds frequencies or periods. And so that's exactly what's going on down here. We've got this E cosine omega and E sine omega. That's just the eccentricity of the orbit, so how squished that circle is. And then the argument of periastron. And so the sine and cosine terms make it cyclical, and we can see how long those cycles take. And that gives us the apsidal period here of somewhere around 50 or 60 years, which is pretty good. And that's consistent with those diagrams we had earlier. Okay, I am going to talk about one more thing before I wrap it up. A very cool result, I think, from our work here is how precise we can refine these apsidal constants based on how much data we have. So how much of an apsidal cycle do we need in observational data points to actually get good values? Does it matter if you have less than a full cycle? Can you still compute them? The answer is yes, but not as accurately as shown here. We simulated some data from a best fit model. So we kind of picked out pieces here and there and created new data sets that follow the same trend to further test this. So we've got a quarter of an apsidal cycle, half, 3/4, and an entire apsidal cycle over so much time. And these show the median value and rough distributions of the individual apsidal constants. We've got K1 and K2 here. So as we get, excuse me, as we get more data, as we move towards half, 3/4, and a full cycle, it's very prominent here. We can see that those distributions are narrowing. That means our values are much more precise. There's a lot less wiggle room in our results. So it definitely helps to have a full apsidal cycle when you are computing these values. All right, I'll wrap it up with a quick summary. So with the eclipsing light curve program, a set of eclipse times, and a good starting point, we can accurately determine these individual apsidal constants, which has never been done before. It's consistent with published values. The average of our constants is consistent with another independent method of computing the average, which is really great. So what's next? What else can we do with this? Why is this important? Well, it's great because it tells us, like I said, about the internal structures of these stars. What we can do is we can compare this to stellar evolution models and see if the models are well representative of that, or if they need a little refinement. We can also look at observational requirements. What kind of precision do we need in our observations when we use telescopes? How precise do our measurements need to be? We can also extend this to other more exotic systems. I showed a 3-body system. Here is that 3-body system again, where we've got the red and the blue points are the primary and secondary stars kind of orbiting each other. And we can see this large motion coming all the way down as the 3rd body is tugging on that orbit a little bit more. So we can test on more exotic systems, and we can add more fitting parameters to determine more fun things. So if you have any questions, I'm happy to answer them now. Thank you very much for your attention, and I hope you enjoyed the talk.
I have a question, if I
Yeah,
may.
sure. Go ahead, Lisa.
All right. So I noticed, you mentioned for one of your stars that you had like 100 years of data.
Yes.
Same telescope, how do you calibrate that data over 100 years?
Right. Very good question. These were not all taken with the same telescope. Some of these, especially on the systems with much older data, we're looking at like the late 1800s when stellar observations were kind of in their infancy. They're using like photographic plates where you have like a piece of glass with a special covering on it that when exposed to light, it shows contrast. So some of those are from that. They're not quite as precise. But with more and more data points, some of these are from individual observations, some of these are from observation campaigns. So maybe somebody did some of these in their backyard. We can kind of take them as a set together and figure out where their median values are, and then that gives us a good idea for where the models will be. But like you said, it can be kind of hard to reconcile the large uncertainties in earlier data points with later ones. Like the test data over here is very close to 0. It's just this like big bunch up here. That's what you get from space telescopes. We want more of that.
Thanks. And I actually think you can kind of see that in your data, right? The spread gets narrower and narrower as time goes on. So I think that's really kind of fun to look at. I'm still monitoring Facebook to see if there's any questions coming in for you. People seem to have enjoyed the talk, so thank you.
Awesome.
All right. And then I guess maybe I will go ahead and do the in the news, and then if anyone can think of any questions for Alex, he'll stick around.
Sounds good to me.
All right.
All right, thanks you guys.
The question did just come in for you
Oh, great.
about are these binaries you're studying all composed of stars similar to the sun, or do they also include stars off the main sequence like giants or dwarves? Although, just remind people who are not astronomers about what dwarves are.
Right, that's a really good question. And to answer it, all of the stars that we're looking at are on the main sequence. None of them are dwarf stars. We don't have like white dwarfs or like red dwarfs that are very, very small. And we don't have any giant stars, although some of the more massive stars like EM-CAR or YSIG, they might be kind of approaching that, because the more massive star you have, the shorter it's going to live, the more quickly it's going to get to the giant phase. As far as being similar to the sun, one of the systems we looked at, V526 SGR, has two stars that are about 1 to 2 solar masses. But the EM-CAR system, I said, was quite a bit more massive. That's around, each star is about 20 times the mass of the sun. So we're looking at a wide range here so we can test our algorithm appropriately. Really good question.
Right. Awesome. All right. I guess I will go ahead and catch you up on some stuff going on in the news. And then, yeah, if you have any questions for Alex, please feel free to chime on in. All right. Just looking to see that everyone can see this. Okay. We all good? So looking over here at Facebook and it's not caught up yet. There we go. That's always so confusing. Okay. So thank you very much, Alex and Rohan, for hosting. It's nice to be back here for Astronomy on Tap San Diego. We have missed you very much over the past year and a half and are glad to be back in your homes with you, especially on this day. Today, September 22nd, 2021, is the autumnal equinox here in the Northern Hemisphere. I've started to try to get into the habit of calling it the September equinox so that we are not completely excluding half of the Earth. So this is the September equinox. And so on this day, the sun is traveling across the celestial equator in its path. And that means on this day, just like for the March equinox, the sun rises in the east, it sets in the west, and you might be thinking it does that every day. But I like to say that the sun rises east-ish and sets west-ish, and it moves north and south of that direction over the course of the year as the Earth is tilted 23.5 degrees on its axis. So what you're noticing here in this image is that what we call the terminator, the line between night and day, as it goes across the Earth, actually goes straight up and down. And that's because the poles of the Earth are parallel to the sun on this day, not tilted towards like it would be in the summer or tilted away like it is in the winter. And so on this day, the hours of daylight and darkness are about equal in length. That's where the term equinox comes from, for equal hours of daylight and darkness. And here in the Northern Hemisphere, we are at the beginning of fall, and in the Southern Hemisphere, they are at the beginning of spring. So in the Southern Hemisphere, they are going on to longer hours of daylight and shorter hours of darkness, where here in the Northern Hemisphere, we are going for shorter hours of daylight and longer nights. And Stu Atkinson on Twitter had tweeted this meme, and I know this meme is done a lot, but this is honestly how I feel about the seasons. I am all just like, bring on the night, bring on the longer hours of darkness. So I really like fall. Astronomers of the Northern Hemisphere are happy, with the possible exception of solar astronomers who have less time with the sun up in the sky. And then I just went around and picked some random news stories that have been promoted over the last few weeks, and they're primarily in the solar system because they have some cool images. And so this is an image from the Mars InSight lander. Now, you might not have heard a lot about InSight. This is not a lander that's taking a lot of pretty pictures. It is trying to give us insight into the interior of Mars. And that's actually where the name comes from. And so this is a spacecraft that is attempting to learn more about the interior layers of Mars, including whether or not Mars has Marsquakes. And so what we're looking here is actually the seismometer, which they have taken off of the spacecraft and placed it down onto the surface of Mars so it can pick up Marsquakes. And on InSight's 1,000th sol, one sol is a 1 day on Mars. On its 1,000th sol, it detected its longest earthquake yet, about a 4.2 magnitude earthquake that lasted for about like an hour and a half. Like it was noticeably detectable for that long. It's the third major quake detected by the Mars InSight lander in the last month. It's had several about 4 point, ish magnitude earthquakes, which for those of us here in Southern California, we know that that can be fairly appreciable. Now, what's interesting about that is that that doesn't necessarily mean that Mars has tectonic plate activity. We don't actually see tectonic plates on Mars. Mars does have a liquid metallic layer in its interior, though, and that's part of what InSight is measuring. And a lot of these quakes seem to have epicenters near a place on the surface of Mars that has a lot of volcanoes. Mars doesn't show any current volcanic activity. Mars has some of the largest volcanoes in the solar system in it, but they've all been dormant in the time we've been watching them. But this does indicate that there is some geological activity still going on underneath the surface. So Mars quakes, they're things that we can actually detect. And then a couple of notes from the Perseverance rover. First of all, just gotta love the pictures that we now take for granted that we get back from Mars. But this is from Perseverance. And they have, we send these rovers to rove around the surface of Mars so that they can be geologists for us, even if we're not there. And what you're seeing here in these little circles are these sort of abrasion tools where it's our way to kind of open up the rock so that we can get samples of it and take pictures of it and try to get a glimpse into the geological history of Mars. And so the Mars rovers do have things like, lasers that they use to carve out little pits for us to study, abrasion tools so you can see how soft or how hard the material is, and trying to do some chemical sampling and analysis in the actual rover itself. But one of the things that Perseverance is doing, which is kind of awesome, is it's actually taking a core sample. And its first attempt at a core sample failed. Apparently, the material was so fine, it couldn't actually keep a hold of it in the borer as it was coming out. But they managed to get, they drove. It's the beauty of having a rover. They drove to a different site and could actually do a sample in another regions. And so if what you're looking in here is at a cored sample of rock from Mars. And so it's inside a titanium collection tube. And they did this the first week of September, so just a few weeks ago. And you might be wondering, why take a sample if this is going to stay on Mars? Like, this rover's not coming back. It doesn't have a way to come back. But one of the things that they're hoping to do with Perseverance is that the idea was that a subsequent mission down the road would actually allow for uh, a rover, perhaps a human astronaut, to come by, pick up the sample, and then either analyze it in situ or actually take it back to Earth. And so this sample has been taken in the hopes that it will eventually be part of a sample return mission in some way. So I had to show you that, the ability to actually take samples. And so now we're going to turn to one more story that has been fascinating me in the news, going from a small rock to what was probably a very large rock. Jupiter got hit. Okay, so I need to just say I can be very happy over giant impacts. I just need to warn you about that. All right, so I can be a little unseemly excited about this. So on September 13th, astronomers, typically amateur astronomers who were just watching Jupiter that night, noticed a flash on Jupiter and an indication of an impact. Now, over the past decade or so, we have now seen Jupiter get hit multiple times. And one of the reasons why we'd never seen it previously is because technology has improved such that you might notice over on the right hand side of the screen, that's video. And so being able to actually just like hook up a webcam or a video camera to your telescope nowadays and just take this streaming video all night long is feasible. Whereas before you had to be hoping that you were actually just taking a picture at the right time. And so now we're able to see these. And what was interesting about this is if you've been outside a little bit later in the evening, you may have noticed that a bright dot up in the sky overhead, and that's Jupiter. And Jupiter has been at just past what we call opposition, directly opposite the sun in the sky from the Earth, so that you see it at its bright. It's basically great for viewing, very favorable conditions for viewing. The website I have down at the bottom of the screen is of an astronomer who is basically accumulating different discovery images of this. And so far, we've seen at least 5 independent discoveries, people finding this before they knew anyone else had known about it. And then multiple detections when people went back and looked at their data after the fact to go see it. And so I just think this is amazing, right? We see these bright flashes. Now, previously, what we've seen impact on Jupiter have been asteroids, the very famous Shoemaker-Levy 9 comet that had been on its way into the sun. Jupiter's gravity caught it, and on its way back around, it broke apart and fell in multiple chunks into Jupiter. But in order for us to see this had to be something like the size of an asteroid so that we could see the flash that it made. So I just had to let you know Jupiter got hit. And Jupiter didn't care. It's probably much more exciting for us than Jupiter because Jupiter's so large that it doesn't make a difference to it at all. But that this sort of cosmic collision does still happen on occasion in the solar system. And there are even some arguments that in order to have a life on a world like Earth, you might need a vacuum cleaner like Jupiter out in the outer part of the solar system to take care of some of this pesky stuff that could impact us. And that's just some of the astronomy stuff currently going on in the news.
That was really awesome. Yeah, I did not know about the Jupiter.
But the Jupiter thing is so great. Like,
Yeah.
aren't you glad you know Jupiter got hit now?
Mhm. My question for you would be, how would Earth be impacted if, do they know what size the asteroid was? How much damage would it have done if it would have impacted Earth instead?
That's a great question. And I haven't been, I wasn't able to find like a definitive analysis that said yet, oh, we think this was a 5 kilometer wide asteroid or something like that. But typically, when we have seen an asteroid impact on Jupiter, it would have been something that would have been a significant event here on the Earth, bigger than like what happened over Chelyabinsk, multiple years ago that lit up the sky. This would have been, when we talk about what caused the Chicxulub impact, the one that they think uh, basically helped help kick off the extinction of the dinosaurs, I guess I should say. They estimate that was about 1 kilometer in size, and that's the sort of thing that we're seeing out here happening. And remember, it's not the impact that's 1 kilometer; it's the impactor. So if you've ever been to a meteor crater, the brilliantly named meteor crater in northern Arizona, it is about 1 kilometer across, but the impactor was significantly smaller. And I think they estimate that would have been like the size of a very large house, maybe like a McMansion, right? A big house. And that also made out of an iron meteorite, which is still sprinkled all over northern Arizona if you know how to find it.
Nice. Wow. So Jupiter really protects us. That's great.
Yeah, it's interesting because obviously a lot of stuff has gotten in, when we take a look at the moon. There's a lot of impacts on it. What's very interesting is that when you take a look at the Earth from space, that's when you start to pick up the impacts, right? Because some of them have been so eroded because we have wind and rain and running water. Some of it's been so eroded flat to the ground that from our perspective, we don't really notice them. It's like, oh, look, this valley in Germany, it's kind of circular, whatever. But when you see it from above, that the perspective from space, it's like, oh, that's a crater. And so there are lots of large impact sites on Earth, but they're old, back from that time that, what do we call it? The age of bombardment, I believe, as the planets were forming early on in the history of the solar system. I gotta love the age of bombardment. I've always loved that name.
Great. That's really nice.
Okay. And so I'm taking a look over on Facebook to see if anyone has any questions. All right.
No, okay. Well, I hope you all enjoyed learning about what is happening in the world of astronomy, or rather the universe of astronomy, and about Eclipse and Binary Stars by Alex Dimoff. And if you haven't already, please follow our social media to stay updated on future talks, which will be coming soon and will be on different topics. And with that, thank you everyone for attending our astronomy webinar from the Astronomy on Tap San Diego chapter. Is there anything else you would like to add, Lisa?
I'm just glad to be back. And what we're going to do is get with our collaborators, see if a date in late October or early November will work the best. And we hope to see all of you back then.
Yep. All right. Well, thank you.